Hi everyone. In the previous lectures, we discussed about some fundamental concepts of communications and also about path loss models. Now we are actually going to discuss and also in the previous lectures we also discussed about how communication happens between two devices. Now we are going to solve, because any part of cellular wireless communications course should mainly deal with cellular communications, because that's more of a complicated problem than other wireless communications like non-cellular communications like Wi-Fi, Bluetooth. They are all little less complicated than what a cellular communication is. Okay, so now we have to understand the motivation for going to cellular communications. So until, if you recall, in 1900s, telephone became a very popular thing. Every house had a telephone. That was the only way that people could stay connected. That mainly speech was transmitted. Mainly people wanted to talk to each other, and telephones was the only thing available at that time. Now the question is, if we have to replace, there were millions of subscribers for a telephone in every country. Every country had lots of telephone subscribers. By 1990s, there were a lot of telephones subscribers across the world. Okay. Now the question is, if I want to replace those telephones by cell phones, what should we do? So we'll start with a city. For example, a city with a population of say 1 million, which is 1 million of population. Okay, I think it translates to 10 lakhs. So that's the population of a city. And then you want to now give, you have to now give cellular access to all those 1 million people. So each one of those should have 1 million, each one of them should have access to a cell phone, which means you have to cater to 1 million users. Okay. Now let's assume that it's a circuit switched FDMA system. So what do I mean by circuit switched is that, so generally when you have two wireless devices communicating with each other, okay, there are two ways in which they can communicate. One is called as a circuit switch system. The other one is called packet switch system. A circuit switch system is one in which once you assign a channel, so for example, I told you when you make a call, a base station normally assigns you a channel for communicating. Now this channel will be there throughout the communications. This channel is given to the users throughout the communications. Even if the two users are not talking to each other, there is no communication happening unless the users switch off the call. Unless they end the communication, terminate the communication, the channel is fully used by these two. So if anyone else tries to access it, they will not get access to that channel. Okay, so that's called as a circuit switch system. And we already know what an FDMA system is. You have to assign, each user is orthogonalized by giving one frequency channel, orthogonal frequency channels. So now let's say we go for an FDMA system. To cater to 1 million subscribers, I may have to give 1 million channels. Okay, if each channel was 30 kilohertz, so 30 kilohertz was the channel. Now into 1 million is 1 is 6. You will need 30 gigahertz. That will be your total channel bandwidth necessary. So at that time, if you recall, for such long distance transmission, we were using around 400 megahertz, 400 megahertz. In fact, it was even lower for AM radios. But this was 1980s, so 400 megahertz, and that was the frequencies we were trying to push. It was in the order of several hundreds of megahertz. But look at the channel bandwidth necessary. So it's impossible to even think of an idea like that using FDMA. Okay, see, right now digital communications had not even come into the picture. So you have to think about engineers in 1980s, how they were transmitting, how they would have tried to solve that problem in 1980s. Okay, digital communication hadn't even come to the picture yet. So there is no TDMA or anything. CDMA is not even there. Just the beginning of a wireless communication. So the analog communication is what they thought of. Okay, now this was the channel, and it was impossible to cater to so many people. So then how do we solve it? So why did they think of this? Because radios were already operational in the cities. So each city used to have a big radio tower, and it used to radiate to many radios. So that was like a classic example of a wireless communication. But the thing was that it was a broadcast channel. So which means information flowed only from one point to the other point. Okay. So if they extended the same idea and they said, okay, let's say we use a broadcast system, then we need a central tower, and that tower has to cater to 1 million subscribers, then we will actually need million channels. The thing about broadcast system is that there was only one bandwidth, one channel that you have to transmit your data in. That's it, because every user is just going to listen to the same radio. Okay. But in case of a cellular system, you needed many channels, because there are several users, and all the users need to transmit they all have different informations. So that's why you need large bandwidth for it. Okay, in a radio channel, in a broadcast system, there is only one-to-many transmission. There is one user, one transmitter, and many receivers, and the data is just fixed. It's always in one band. For a given radio station, it's always in one band. Okay, so now the problem was, how do we replace telephones and make it as accessible like a landline telephone, okay, and still not run into the problems of huge bandwidth and so on. So that was the problem that engineers were trying to solve at that time. So the question was, the available channels were finite and limited. We had only a fewer number of channels, few channels. Okay. Now, how can you actually cater to a large number of subscribers with just a finite number of channels, where the number of users, I'll call it C, can be much greater than the number of channels S. S here is the number of channels. Okay, it can be much greater. How do we solve that problem? Second thing is that once you go wireless, you can actually move. So now, as you start moving from your location, whether you are on a car, on a bike, or on a pedestrian regular walk, your phone should not have a call disconnected. You should still be able to connect. So that was the second problem that they had to solve. So how do we actually account for mobility? So if your cell phones, especially cellular communications, they take in mobility into account. So even if you are moving, you will actually have access to the communications. Okay, moving vehicles, obviously. So when you are even on a moving vehicle, you should be able to account for that as well. Okay, so now in 1979, a very famous paper was written by McDonald. Again, see, the ideas were there for a decade, but he had to consolidate everything and put all these questions answer all these questions and in a proper mathematical framework. It's a landmark paper in the field of cellular communications. He tries to answer all these questions. Okay, so the idea was pretty simple. So like all good ideas, most of the good ideas are actually pretty simple. So what he said is, now instead of just having one base station radiating power to all the cellular phones, in which case the problem was that we needed large number of channels. The number of channels necessary, let's say C, was really large. Okay, or sorry, S is the number of channels. The number of channels necessary was equal to the number of users in the system. C is the number of users in the system. Okay, that was the problem. Now we said, no, instead of doing that, let's divide the whole city into small regions called cells. Okay, now each cell will have a small base station, a local base station, which will radiate with a much lower power compared to, now initially we had one central base station here radiating to the whole city. Instead, we'll have one small base station radiating within a smaller region. So that was the plan that was thought of. Okay, now if you do that, then he thought of a very interesting problem that, look, when you had radios, for example, in radios where we had different states within our country, each base station in different cities were using the same frequencies, okay, but they were broadcasting different information. They were using the same frequency channels, but they were broadcasting different information. And the reason why two radio stations were not interfering were because the region of coverage for a radio station was actually much smaller than a corresponding radio station which was transmitting in the same frequency. By the time that signal reaches here, it would have decayed down significantly. Okay, so the radio stations were in fact transmitting many radio stations in different cities were transmitting in the same frequency. The reason why the other radio stations were not interfering with the current one, because they were geographically so far apart. Okay, so we know that from the path loss models, the power decays down exponentially. So since they are geographically so far apart, I don't have to worry about the other base station, the radio station which is transmitting. So he extended the same idea to cellular concept as well. He said, let's divide the city into small regions and assign same frequency channels to two different regions. You choose the regions such that they are physically far apart, such that even if the power that is radiated in this, by the time it reaches here, it would become negligibly small, so that it will just look like noise. It just gets buried in noise. Okay, so if I'm going to use same frequency, I'm going to have interference. From here, some other user is going to be talking something, I might end up listening that. Okay, or the base station might end up picking that. Okay, so the problem was this solution, which the solution to this problem was involved dividing regions into small regions, dividing a big region into small regions called cells, and reuse the frequency again. So this concept is called frequency reuse. So he said, I can reuse the same frequency m number of times within a given region. Okay, if I reuse it more number of times, which means I'm supporting that many number of new users. So that way I could increase the number of users. So that was the very clean and very simple solution for that problem. So he thought, now if I've shown here, A here corresponds to a certain number of channels. So what he said is, let's say S be the total number of channels. Now what I'm going to do is that I'll divide this entire region into small cells, and I'm going to assign unique frequencies to a set of cells called as a cluster. He just called the few group of cells as a cluster, and to each cell he is going to assign a fixed number of channels. Okay, and then he is going to reuse these frequencies again at a different region, geographically at a different region. Okay, so that way, now if you see, he's catering to more number of users using the same frequency, and he's relying on the fact that when I say he, the McDonald is relying on the fact that the two base stations are so far apart that they don't interfere with each other. Okay, so that's the problem. So base station A, even if here the base station is transmitting the same frequency, a mobile phone in this region will not receive a signal transmitted from here. Okay, so that's an interfering signal, and it will not receive if the two base stations are sufficiently far apart. So that's the first concept. So to just mathematize it, what he did was he started with S is the total number of channels available. He said, I'm going to divide this region into small cells, and I'm going to group few number of cells, n such cells, to form a cluster. So let's say we had a big region, I'm dividing it into small number of cells, a large number of cells, and I'm going to group n such cells, and I'm going to call that as a cluster. Okay, now in these n cells I'm going to equally divide my channels. So each cell in a cluster will get S by K channels. Okay, so now because now this entire region is divided into cells, now that I've grouped the cells into clusters, I can say that this entire region is divided into m such clusters. Okay, each cluster has n cells, and we have m such clusters. So the total number of cells is m into n. Okay, m into n will be the total number of cells, and n is the number of clusters, and n is the number of cells in a cluster, is the cluster size or number of cells in a cluster, and m is the total number of clusters. Okay, now if you recall, each cluster uses S channels, because I'm taking S channels and dividing it into within a cluster. But now essentially each cluster uses S channels, and there are m such clusters. So the total number of channels, let me just say this again. So if m is the number of clusters, I'm going to reuse the frequency m times. Okay, so the total number of users that I can support is equal to the number of channels in this example. That will be simply S into m. Okay, because in the n cells I can support S users, because I have S channels simultaneously. I can support S users. The word simultaneous is very important. We will later see when we talk about trunking and grade of service why the word simultaneous is very, very important. Okay, at any instant I can support S number of users in n cells. Okay, so the total number of users that I can support is S into m. Now if you look at this equation here, okay, I began with S channels, but I'm going to define a new term called capacity here. Here this is user capacity, whereas in Shannon theorem it was channel capacity. The user capacity is the total number of users that you can support in a cellular system, and that is simply equal to S times m. S is the number of channels available, and m is the number of clusters. Okay, so now this is a very interesting result. So all it says is, if I just increase the number of clusters, then I can actually increase the channel capacity significantly. So I'm just going to make m tend to infinity, then S into m will also tend to infinity, C will also tend to infinity. So which means the number of users I can support will become infinity. So let me remind you that we have started with a finite number of channels. S is still finite. I just increase the cluster size. Okay, I just increase the number of clusters. Okay, so that should sound very intuitive, because, so for example, all I need to do is that, let me just show it on a text. So all I need to do is that, so I can take a region, a big region, divide it into smaller and smaller cells. I can make the area of the cells much smaller. Okay, so then I'll need more number of clusters. So if I just reduce the radius of a cell, if I make even smaller cells here, I can make the cells even smaller. Then of course I'm going to reduce the number of the size of a cell is reducing, which means I'll need more clusters to fill out this entire area. The area is fixed. I'll need more clusters to fill out the area. Okay, now the question is, if I make this cell size smaller, infinitely smaller, then I'll need infinitely more number of clusters to fill out this entire region. So m will tend to infinity. If I make the radius of a single cell or the area of a single cell go to 0, which means you will need infinite number of such clusters to fill out this area, which means m tends to infinity, which means we can support a large number of users. Of course, this doesn't come for free. If I'm going to reduce the cell size, I'll also need more number of base stations, more radiating elements per cell. So that's cost. So of course, there is no free lunch. So if you're going to spend money, you're going to get better and better capacity. Okay, so it fundamentally came down to that. So he said we can start with a finite cells. So eventually the decision is made on what is the money that for example, a cellular operator, if he wants to give subscription to a certain number of users in a city, he is just going to plan out on how many cells he has to divide, what is the money he is ready to spend. All those things will be kept in mind, and accordingly he'll decide it. Okay, so here in the McDonald's paper, he just began answering this question. Okay, if I reuse my frequency with a finite number of channels, I can support an extremely large number of users by using the concept of frequency reuse. Okay, so then the same questions arise what was there in telephone communications, same thing arised in cellular as well. Okay, in a telephone region, say for example, when you start laying wire to a certain house in a region, then everybody near that region will start applying for a subscription, and everyone starts getting the wired connection. Okay, so telephone connections happen that way. First you dig to some house who can afford it, then every other house will start getting the telephone connection. It becomes easier to allot it. Now the same thing, they said, okay, you are going to initially you will have certain number of subscribers, but the subscriber count is going to rise. How are we going to account for that? So that's the other next question he had to answer. So he said, I'm going to apply the same concept that I applied for the entire region to a single cell. So I'll take a single cell and divide it into smaller cells. If the number of subscribers within the cell starts increasing, okay, then I'll just apply the concept of cell splitting to the single cell itself. This is called cell splitting. It's going to take a single cell, split it into smaller cells, and apply the same concepts of frequency reuse for the cell itself. Okay, so using the concept of frequency reuse and cell splitting, he can solve this problem of cellular communications. Okay, which means I'll start with a finite number of channels, but I can actually serve a large number of customers using or subscribers using a finite number of channels. Okay, so this was the fundamental problem of cellular communication. So he said, I'll begin with this. Now if you see, the small cell sizes has reduced. We initially began with large cells, what I've shown here as an example. Okay, A, B, C, D here represents channels. Okay, A represents the group of channels and so on. Okay, now we made the cells smaller and we keep applying it to every region. If the number of subscribers keep increasing in every region, then here the example shown here, we have actually applied cell splitting to almost all the regions. So initially we began with large cells like this. Okay, then as shown here, we have applied cell splitting to one region. Now eventually if every region starts then the number of subscribers start increasing in every region, then we'll have to do cell splitting for every region. So that will significantly increase the number of users that you can support. Okay, so this was the basic idea, and McDonald didn't stop with this. He gave a proper mathematical analysis for interference. How do you study interference? Because now the problem is, if I'm going to reuse the frequency again, the main problem is a cell phone in this region, a cell phone in this cell can hear what this guy is transmitting, what this guy is transmitting, because everywhere there is A, or what this guy is transmitting and so on, or what this guy is transmitting. Okay, the cell phone is now going to hear all this. So anything that is not wanted by this, not intended for the cell phone, is called noise or interference in this case. Okay, so cellular systems will have to deal with a new problem now. Of course, we could solve the problem of increasing the customers or giving more subscribers by using frequency reuse. It looked like a neat solution, but we have introduced a new problem, which is interference. Okay, because now there are many different users, different base stations transmitting at the same frequency, and now we are going to hear that. Okay, your cell phone is prone to hearing all those things. So how do we as an engineer start deal with this problem, and how do we design our systems that they work even in the presence of interference? Okay, so the mathematics part of it I'll probably discuss it in the next lecture. Okay, so McDonald didn't stop with it. He actually properly gave a mathematical analysis of a cellular communication, how to actually deal with the interference and all that. So that we'll discuss in the next class.